Good afternoon, students. Myself, Dr. Divya Ghildial, in continuation with my lecture series for AKTU B.Tech first year Engineering Physics syllabus. Today, I will be briefing you in wave optics about diffraction. Now, diffraction of light is shown by the wave nature of light. So let us first have a look at your syllabus for diffraction. What is the syllabus? Syllabus in diffraction speaks about Fraunhofer diffraction at single slit and double slit. Only two cases of diffraction, single slit and double slit. The condition for absent spectra, usually the question is, what is the condition for missing order spectra in diffraction? Diffraction grating, you also have an experiment on the same in your physics lab. Spectra with grating, dispersive power of grating, resolving power of grating, Rayleigh's criteria of resolution, and resolving power of grating. So what all is asked? In section C, 10-mark question, you are asked to derive an intensity distribution expression for diffraction due to single slit or double slit. The derivation for both the cases is same, except that in double slit, a factor of 2 gets introduced. In section A, a question, one-line question is, what is the reason for certain colors not getting observed in the spectra obtained because of diffraction? What is diffraction grating? How do you obtain a spectra with a grating? Define dispersive power and numerical with same. Define resolving power, numerical with same. What is Rayleigh criteria of resolution? Discuss the same, and a numerical on resolving power of grating. So let me begin with the syllabus. Firstly, what is diffraction? The bending of light around apertures and obstacles is known as diffraction. There is a difference between diffraction of light and scattering of light. They both are not the same phenomena. Your AKTU syllabus expects you to know about diffraction. So the phenomena of bending of light around corners or obstacles and their spreading into the geometrical shadow of an object is known as diffraction. There are two types of diffractions. This is a very favorite question of section A. Differentiate between Fresnel and Fraunhofer class of diffraction, a 2-mark question. In Fresnel class, the source or screen both are at finite distance from the obstacle. In Fraunhofer class, source and screen both are at infinite distance from the obstacle. In Fresnel class, the distances are important, whereas in Fraunhofer class, the inclinations, that is angle theta, is more important. In Fresnel class, the incident wavefront will be spherical or cylindrical, whereas in Fraunhofer class of diffraction, it is usually plain. It is always not more than a 2-mark question. So one extra has been given to you. Now, before we start deriving an expression for intensity due to single slit of a diffraction, we need to understand the formula for resultant due to n number of diffraction rays. So first, take a printout of this PDF file which is given in the comment box and start following step by step with me of how I have derived a formula for resultant due to n number of rays which are undergoing diffraction. So let us begin with n number of simple harmonic vibrations. They all are having equal amplitude A and a common phase difference of del between the successive vibrations. Now, What is our target? See here, you will be requiring lot of your intermediate formulas of tan and sine and cos. I have given them here to you in the notes so that you do not need to refer any book. And if you want, for your main exam, you can skip out the basic formulas. They have just been given so that step-by-step derivation is clear to you. This derivation is important. It will be a 10-mark question. Derive an expression for intensity due to single slit or double slit. There you will need to understand first how the resultant comes. So let us begin. See, these are n number of harmonic waves here. 1, 2, 3, 4, 5 till here n number. They are having amplitude A and a proper phase difference del. For the first, second 2 del, third del. Now we know from the basics of vector calculus that the resultant is given by joining the tail of the first vector to the tip of the last vector. This gives the resultant. So to find the resultant amplitude, a polygon is any geometrical figure with n number of sides. It is constructed, and now we have resolved this component along the x direction and the y direction. So we will take all the x direction components of cos theta. We do this in vector analysis. So you don't need to write detailed description. This is just vector analysis, simple, where we are resolving the components along the horizontal and perpendicular directions. And then to find out the resultant, we will take the square root of the square quantities of this. So r cos theta, the horizontal component, comes out as A plus A cos phi here, A cos phi, A cos 2 phi, A cos 3 phi, so and so till A cos n minus 1 del. Sorry, del, not phi. Now the perpendicular components, that is sine. So r sine phi is equal to A sine del plus A sine 2 del plus A n minus 1 del. Now, what we will do is we will simplify this equation further. So in equation 1, here left hand side, we will introduce the sine term. So if I multiply left hand side and right hand side by the same expression, it makes no difference. So this trick of mathematics I will use. I will multiply my equation 1 by 2 sine del phi by 2. By doing this, what have I actually done? I have introduced sine in this expression. So I get 2 sine del by 2 plus 2 sine del by 2 cos del, 2 sine del by 2 cos 2 del, plus so on till n minus 1 del. Now from trigonometry, I know that 2 sine A cos B is equal to sine A plus B plus sine A minus B. Now I will use this formula to simplify this expression of mine here. See, I am getting an idea of what actually I am doing. 2 sine A cos B, sine A cos B. I will use this formula and write it down in a more simplified form as 2 sine del by 2 plus sine 3 del by 2 minus sine del by 2 plus sine 5 del by 2 minus sine 3 del by 2, so on till sine n minus 1, n minus 3 by 2 del. I have used this formula of trigonometry. Here is this is say sine A, and this is my cos B. So I used A del by 2 and B del. So I get 3 del by 2 when I add them and del by 2 when I subtract them. Hope it is clear. Proceeding further, this is very simple. Only the components have been resolved in horizontal and vertical direction, and then their resultant sum has been taken. All this we are only doing so that our target of finding an expression for intensity due to single slit in diffraction can be fulfilled here. Now, I simplify this expression further, take the sum, and I get 2r cos phi equal to a sine n del by 2 cos n minus 1 del by 2 divided by sine del by 2. In a very similar manner, this I did with this expression, equation 1. I can do the very same thing with equation 2. Here, cos is missing. So what I will do, I will multiply equation 2 by, equation 2 by 2 sine del by 2, and simplifying it, the vertical component comes out as r sine phi is equal to a sine n del by 2 sine n minus 1 by 2 del divided by sine del by 2. Now, we know from vector analysis that if we need a resultant vector, we take under root and square both the components. So we get r square is equal to a square sine square n del by 2 divided by sine square del by 2. And resultant becomes a sine n phi by 2 divided by sine del by 2. And tan phi becomes equal to tan n minus 1 del by 2. And the phase angle phi, if we compare from this formula, tan comes from where? Sine theta divided by cos, sine phi divided by cos phi. This gives me the value of tan here. Phi is n minus 1 del by 2. Now, since x and del are very small, n is infinitely large, such that NA can be taken as a resultant amplitude capital A and n del equal to 2x. So my resultant formula becomes equal to a resultant due to the vertical and horizontal components of n number of harmonic waves becomes equal to NA sine x by x. Now, we will do a very small modification in this formula. NA, we will take as the resultant amplitude capital A due to n number of harmonic waves. And if theta is very small, then according to mathematics, I can take approximation of sine theta as theta. This is from mathematics. So instead, I can take this as an approximation, and simply I can write it down as n is as n is hence x very small. Okay, you can just sine x by x. The resultant amplitude expression becomes equal to a sine x by x. This approximation we will take when we will do the single slit case. This is the formula for resultant due to n number of harmonic waves, where A is your total amplitude due to n number of waves. Now we begin with the syllabus, the first heading, diffraction due to single slit. Let us see. This comes as a 10-mark question in your AKTU paper. Derive an expression for intensity distribution due to Fraunhofer diffraction by single slit and show that the intensity of first subsidiary maxima is about 4.5% of that of the principal maximum. This is a very important question. And for understanding this expression, deriving it, it will be of 10 marks, not less than that. First, understand this diagram. See, have a look at this diagram. Can you make out? This is the single slit which I am talking about. Only one slit. S is your source of light. This lens L1 has been put here so that the rays of light falling on it, the diverging wavefronts, they get a direction. And Since diffraction means bending of light around apertures and obstacles, I will make my light fall at the aperture or the opening. And then a second lens has been put to collect these rays and make them fall on a screen here. So can you note there is no ray here in between, because this is a diagram of diffraction due to single slit. That means only one slit in my setup. For double slit, only a very minor change takes place in the diagram. Instead of one slit, you will show two slits in the diagram. See, both are very important. Single slit and double slit. Here, double slit. See, now there are two slits, S1 and S2. In single slit, you took only one slit. Now, what have we to find? We have to find an expression for intensity due to single slit. Let us begin from source S. Light is incident on as a plane wavefront on the slit AB. From Huygens theory of wavefront, we get a large number of secondary waves. The undeviated rays from AB are focused at C and on the lens L2, and the other rays are diffracted through an angle theta and are focused at P. Rays from the other end are focused at C. Clear from the diagram? Now let us start deriving an expression. We begin with path difference between the rays. In order to get an expression for path difference, we drop a perpendicular and we use the formula for sine theta, perpendicular upon hypotenuse. So Bn equals to AB sine theta. AB is your slit width represented as small e here. Many times they represent slit width as A also, but here I have taken small e. So Bn equals to E sine theta, where E is slit width. What is phase difference? Phase difference is equal to 2 pi by lambda into path difference Bn. Let AB be divided into n equal parts that may be infinitely large number of point sources of secondary wavelets between A and B. So the phase difference between any two consecutive parts when it comes to n will be equal to 1 upon n into 2 pi by lambda E sine theta equal to del. In order to find the resultant amplitude of n such vibrations, each of amplitude A and phase difference del between successive vibrations, the resultant intensity will be given by R is equal to A sine n del by 2 divided by sine del by 2. What is actually this del factor here? Look at the expression above here. See, del comes out as here, del. Put del here as pi E sine theta by lambda, and this 2 has got cancelled. So this becomes equal to sine pi E sine theta by lambda and sine pi E sine theta by lambda. We have put this del value here. So putting, and now what we will do, pi E sine theta, we will put it equal to alpha. We are doing all this only to make the expression look simple. That is all. So that it looks very simple. So we are taking this effort. Okay. Now we put this equal to alpha, and then we get R is equal to A sine alpha divided by sine alpha by n. This is what I was right now talking, that this alpha by n. We will approximate this quantity, that for large values of n, x upon n is very small, and therefore this sine term can be approximated to alpha by n. And we get R is equal to NA sine alpha by alpha. This is the expression where NA I have put equal to resultant in amplitude, is an expression for resultant intensity is always proportional to the square of amplitude. Hence, intensity due to single slit is equal to A square sine alpha by alpha whole square. Here, alpha is, I told you, showed you upstairs, up here, alpha is pi e sine theta by lambda. Now, condition for maxima and minima. That means what type of spectra we will get on the screen. So we have found an expression for resultant intensity R equal to A sine alpha upon alpha. We know from trigonometry and mathematics that the series of sine is 1 minus x cubed by 3 factorial plus x to the power of 5 by 5 factorial minus x to the power of 7 by 7 factorial. So we will use this formula of sine alpha here, and alpha here we have this alpha and the alpha up are common. They will get cancelled and you will get the expression for resultant intensity in this simplified form. R will be maximum if negative terms in the above equation vanish. This will only be possible when alpha is equal to 0. You remember, alpha we had taken pi lambda e sine theta equal to 0 or theta equal to 0. So the resultant intensity at P will be maximum for theta equal to 0, and it is called the principal maxima, and intensity of the principal maxima equals A square. For minima, sine alpha will be equal to 0, but alpha cannot be 0, that is alpha equal to plus minus m pi. We will put this condition for this expression to be equal to 0. Not forgetting that alpha what we have taken is pi e sine theta by lambda was my alpha. So alpha will come out 0 at these points, plus minus m pi. So E sine theta equal to plus minus m lambda will be the position of minima. We know that diffraction spectra consists of a principal maxima followed by secondary maxima and minima. So what are we actually trying to do? See, principal maxima, resultant intensity at P will be maximum for theta equal to 0 and is called principal maxima. This is the one. For position of minima, we are trying to find out. So it becomes E sine theta equal to plus minus lambda. We will get the minima points here. And for secondary maxima, the condition may be obtained by differentiating the intensity expression I equal to A square sine alpha by alpha square. This was my expression for intensity due to single slit, which I just derived. Now I am trying to find out an expression for secondary maxima and minima. This I will get by differentiating the intensity expression with respect to alpha. So this is what we have done. Di by d alpha becomes equal to d by d alpha into a square sine alpha by alpha whole square, and the differentiation for numerator upon denominator. What is the formula? D by dx of denominator into numerator minus numerator into d by dx of denominator divided by denominator square. This formula we have used. Now, see, multiple of two terms is 0. That means either this term sine alpha by alpha is 0 or alpha cos alpha minus sine alpha is 0. See, this will be, we are taking the condition for secondary maxima, and this multiplied by this is coming equal to 0. This condition, according to mathematics, will only be possible when either this is 0 or this term is 0. So either sine alpha by alpha is 0 or alpha cos alpha minus sine alpha is 0. So what we have done, we have alpha cos alpha minus sine alpha. Divide sine alpha by cos alpha, it becomes equal to tan alpha equal to alpha. So the position where these 2 points intersect gives you the position of principal maxima. So the position of secondary maxima is given by alpha equal to tan alpha. So we have plotted these points on the graph paper. This is a tan curve, tan plot, and y equal to alpha is a straight line passing through the origin, y equal to mx plus c, where this is a straight line, and y equal to tan alpha. Wherever these points intersect, they give us the position of principal maxima, that is alpha equal to 0 plus minus 3 pi by 2 plus minus 5 pi by 2 plus minus 7 pi by 2 gives the position of first secondary maxima, second secondary maxima, etc. So the intensity for first secondary maxima, where you put alpha equal to 3 pi by 2, becomes equal to 4 by 9 pi square a square. Intensity for secondary maxima is 4 by 25 pi square a square. Hence, relative intensities, this is the central maxima, is given by I1 is to 4 by 9 pi square divided by 4 by 25 pi square. And this is very important. It is asked, it is a 10-mark question. Please remember that. Thank you. Love.